All right, well, hopefully the audio holds together long enough to turn it over to Robert. Thanks everybody for attending the office hours. This is a continuation of the application discussion that we had last week. Robert is going to get into more detail on the Transactive Control and Coordination agent, and then we'll be available for any other questions around agents, or applications that you're interested in, or talking about building applications in Voltron. He's got a lot of experience with that, as well as with deploying applications and Voltron in different environments on different operating systems. So if you've got questions around that, you can provide that as well. So with that, I will turn it over to Robert. Thanks for continuing with part 2.
Sure, let me go over here. So can you guys see my screen?
Yeah, I can see it.
We can.
Okay, so I'm just going to go through, this is a slide that Srinivas presented a while back, or a slide deck on TCC. I'm going to go through this, and then hopefully we can talk just a little bit more about actually deploying the agent in the real world and some of the stuff that we're doing to make that a little easier. It's a pretty complex system of agents, and we've recognized that, and we're trying to make deployment of this application or set of applications easier for people. So the Transactive Control and Coordination application basically uses signals from external markets, and this can be price signals or other driving signals that basically make the applications modify the controls to manage the energy consumption of the devices to some desired level based on those signals and their flexibility. And that flexibility is determined based on some modeling that's done in the agent. So currently we've deployed this application for several types of devices, including rooftop air conditioning units, air handling units, with VAV boxes and lighting systems. A couple of the use cases that we've deployed for: load shaping, and then dynamic incentives. So I'm just going to kind of fill this out as we here so that we can kind of talk through it. So as I mentioned, the TCC agents use models to derive the flexibility of the different components. And for instance, a VAV box would use parameters such as outside air temperature, zone temperature, and the set point to determine the need for cooling. And basically, previously, we would do these models in an offline manner. That means that we would use some data, train the models, and then deploy TCC for some period of time, and then periodically review those models and update the parameters if needed. We've since then developed an agent that actually allows for this to happen in an automated way, so that you can deploy this agent along with the TCC VAV agents, and it will automatically retrain the agent periodically and then communicate those new model coefficients to the agent. So as I mentioned, those models are used to determine some commodity, the flexibility versus the flexibility of basically a needed commodity. For VAVs, that's cooling, versus some pricing signal or some other signal. So as the TCC moves through a market cycle, and it utilizes at the building level the Voltron market, which could be a whole nother topic of discussion. Each one of these zone level agents bids in a price capacity curve, basically describing their cooling flexibility versus price. Now that curve is then aggregated at the AHU level to an overall need for cooling for the AHU. The AHU agent then utilizes another model, which is built for that AHU, similarly to the VAV model, but of course a different form, to translate that into some need for electricity. And then based on the supply curve, the market clears a price, and that price is then propagated back down to those individual TCC agents, which modify their controls. For the VAV agents, that would be their zone temperature set points. For the lighting agents, that would be the dimming level for the lighting in the zone, to try to consume the cleared quantity based on that cleared price. And again, if there's any questions or comments during this, feel free to ask at any time if anything's unclear or you just want to have a discussion about it. That'd be great. So that's the basic TCC workflow, is develop a model. When you deploy the agents during the TCC, they generate their price capacity curves. There's some level of aggregation for those curves, and that's translated into an overall demand for either electricity or some other commodity that is clear based on the supply curve, the intersection of the demand and supply curve, and that supply curve can be a fixed demand curve to limit the electricity at the building level. It could be a fixed price curve. It could also be some other type of supply curve that you know the form based on the signal from the utility or something. So this is just going to talk a little bit about the models, and I really was hoping that Sen Huang would join us. He helped to develop the reduced order models that we utilize for the TCC applications. So he'd be able to talk on this point a little more thoroughly than I can. Essentially, we utilize data and these data-driven models, and the models are semi-physics based. So they have some form that is based on heat transfer in the zones for the VAV. And as you can see here, we've developed this model and validated this prediction. It's pretty good throughout the day. So this is a look at just generally what the price capacity curve for any of the TCC agents would look like. Basically, you have a minimum and maximum price that is calculated based on the average of some price, average of the price over a certain period, and this could be the average price over the previous 24 hours or some other period. And then we have this K, which is a user-defined factor, which basically allows you to dilate or expand this curve around the mean price. And as you can see, if you make K 0, you're going to get more savings, and a K of greater than 1 will elicit more comfort. So here is the reduced order model that's used for the VAV. As you can see, this is based on the minimum and maximum zone airflow rates, temperature set points, zone and outdoor air temperature, and zone discharge air temperature. So each one of the VAV agents, and what's kind of unique about this application is that it's very distributed. So each device is represented on the platform by one agent that's bidding in that price capacity curve and then modifying their control to try to elicit or consume the cleared quantity. And as I mentioned previously, that need for cooling at the VAV level is then aggregated up, and this is the model form the AHU chiller agent utilizes to calculate both a fan power and a chiller power to bid into the electricity market. And when I'm saying, you know, these different markets, and the dimming light, the dimmable lighting level for the lighting agents is based on, it's a very simple model, just based on the minimum and maximum allowable dimming level. And I'm going to skip over this guy. This is for the RTU. It's a little complicated. So let's skip over that. This is an overview of just kind of how we would deploy this in a co-simulation environment, where we have our applications or TCC agents running, and then we might have a building over here running TCC, communicating with real hardware, and then a simulated building also running TCC and communicating with some simulation engine. This allows us to deploy this and test this with, you know, a lot more buildings than we would actually be able to play with in the real world. Whereas on campus, we have 10 or 12 buildings that are part of our transactive network. We can scale this and add as many simulation buildings as we want to verify that this is actually a scalable solution. I don't want to go over any of this stuff. So this just shows kind of how the market clearing process works. You'll have bids from the individual TCC agents for certain commodities, and for VAVs, that's like I mentioned, airflow or needed cooling. Those are aggregated up to the HU level. And then the Voltron market service actually is a consensus-based market that clears based on the intersection of the supply and demand curve. And you would have a clearing power or quantity and a clearing price. And that would translate into control actions for the individual TCC agents. So let's keep going. Cool, and we can look at some results here. This is for a building that we've deployed the intelligent load control on. This is where it gets a little bit interesting, and we can talk a little bit more about this. So down here at the bottom, you have the VAVs, and these are TCC agents that are running and represent each one of the different zones in the building. So these individual VAV agents are communicating through the message bus, and periodically, when the market signals, submitting a demand curve, price capacity curve for cooling air. And each one of these VAVs is associated with a different air market that's tied to their AHU. So that air market then aggregates that demand, and it's communicated to the AHU chiller agent, and the AHU chiller agent then converts that need for cooling into a price capacity curve for electricity. All of the agents here, the chiller agents and the lighting agents, then communicate that to the electricity market, where that is again aggregated, and the Voltron market service then clears the market based on the supply, the intersection of the supply and demand curve, and that supply curve can be fixed price, fixed demand, or some other supply curve sent by some outside source that could be a utility or some other application that you've designed to send that signal. So this is talking about a simulation test that we did. You can see that it has 25 VAV agents, 4 AHU agents, 21 lighting agents. It's running in Energy Plus, utilizes the Voltron market service. And again, it's just talking about the zone level stuff here. So I think we've covered that pretty well. Look at a few results here. So as you can see, we have the response for one of our buildings based on different pricing signals. And you can see that here, this top curve is the baseline. And as the price increases, the corresponding consumption of the building decreases, showing that basically the TCC applications at the building level are price responsive. And also you can see how the zone temperatures are affected by each of the different prices. So you can see that at the baseline, we are having this kind of lower price. And then as the prices increase, you can see that the zone temperatures are allowed to increase slightly. Still within comfort ranges though. Here is another use case, very similar, where we did a demand limit. Essentially, the demand limit is the supply curve coming from into the market is going to be a fixed demand curve. And the idea of this is to limit the amount of demand that at the building level. So it's essentially choosing a target for the building and trying to have these distributed agents coordinate to consume their cleared quantity to achieve the overall goal of keeping the building demand below this limit. As you can see, we were fairly successful. We exceeded it a little bit, but for the most part, managed the building demand to the limit. And you can see here some of the zone temperature responses. Here's our prescribed comfort range. So not a lot of deviation. And you can see that when we started to actually approach that demand limit, that's when the temperature started to be modified. So essentially prior to the demand limit or hitting that demand limit, the control is nominal. We're essentially controlling to the normal set points, and then afterwards, we are actually taking some action. The individual TCC agents are responding to that price that's cleared to reach the target. So I think that I'm pretty good with that. I don't think Sen signed on, so I don't really want to talk much more about the models, but I would like to talk about the code a little bit and where it is and then the structure. So the Voltron, the TCC code lives in the Voltron GS repository, and it's composed of 3 parts really. So we have the market agents. And so each one of these agents represents a different device or portion of the overall building capacity. So as you can see, we have the VAV agent, we have an RTU agent for heat pumps and rooftop units, a lighting agent, an AHU agent. And then an uncontrollable load agent, which represents the part of the building load that is non-controllable, that is basically the base load. These market agents are built out of two main components. They are built on a base class, which is here. This is the transactive base class. It handles most of the input output and market interactions. And they're also built around a model. And we've put in a pretty interesting, I wouldn't say interesting, but extensible model structure. So the model structure allows one, through configuration, to essentially gives the user the ability to easily add or swap models for different components by just extending this VAV or RTU class. And so it's actually a pretty easy way to develop and implement your own model for predicting the quantity of interest in a pretty easy way. And if anyone has any questions about any of that, they can contact me. The last part of the TCC structure is going to be the Voltron market service. And that lives in this mixed market service agent. This is a consensus-based market that basically handles a lot of the callbacks and other interactions for doing the aggregation of curves and then finding the intersection of supply and demand curve to clear the market. And this was written by Edward Ellis a couple years back. It's been modified and extended a little bit, but it's primarily still functionally the same Voltron market service. So I think that is primarily all I wanted to cover. And I'd sure like to open up the floor for questions or discussions or any other input that people might have.
Can you hear me?
Yeah.
Okay, Sam Delay. So, in running a control system for a building, in the past, we had to come up with priorities for zones so that we would have shed zones where, there's certain areas where they're very active and maybe you have a library that's very inactive. And so we would approach it from a shed zone standpoint. I'm wondering how that compares to the agent view as one point. And the second one I might ask is about the comfort limits. So on your price curve, how do you know there's not just some discontinuity? For instance, one person might have a 75-degree set point maximum. Another one has 78 or doesn't care at all. And so there's a little bit of a zone interaction with personal comfort. And I guess I'd ask the third question, and that's opt out. So is there a facility in here to opt out of control of some of these things so that you can, say you got a special occasion? For instance, Mother's Day is coming up on Sunday. So if you got a house full of people, you might not want to have the same control strategy. You might want to opt out for a period of time. So thanks.
Yeah, so I guess, can you do one at a time? Ask me your first question again.
Okay, first of all is agent priority. So for different zones, sometimes zones, have different functions, and a library might not be the same as your executive office, or let's say it's a judge in a office building. And we had a judge in an office building that wouldn't tolerate much of anything, and then the secretary, staff, or whatever might have to tolerate everything. So what about zones?
So there's a couple of ways that you can handle that within this application. So there is a prescribed minimum and maximum zone temperature. that's used for the controls, as well as predicting the quantity, the need for cooling. And so that minimum and maximum can be adjusted. And so that's one way to prioritize a zone. You could say, okay, for this zone, I'm only going to allow such a increase or decrease. So that would be, maybe you're saying, okay, here's my nominal, and then I'm going to do 1 degree around the nominal plus or minus based on the price. Or if you're saying, you know what, I really just don't want this zone to be controlled at all. I want it to keep the nominal set point all the time, but I still want it to participate in the market. Then what you can do is you can make the minimum and maximum within the application the same value as the nominal. That way it'll still produce a demand curve so that its load can be accounted for in the market, but the control and the prediction will be a flat line. So that would allow you to essentially exempt that zone from control while still leaving it within the transactive framework.
Okay, that sounds good.
Also, one other thing to mention is the models that are produced. Although they're reduced order models, so they're really relatively simple. They are physics based, somewhat physics based, and they're data driven. So if you have a judge's office, for instance, their predictions for demand and therefore how the set point is going to affect that need for or consumption is going to be driven by the past data, which also helps account for, some of the irregularities, or not irregularities, but occupant tendencies, right? I hope that answered your first question well.
Okay. So, well, I guess along with the priority is the timing. So, let's just assume we have a judge and he doesn't work many hours in the day. And maybe he's in his office about 4 hours a day. He's very low tolerance, but during the other 4 hours, how do you set the time parameters?
I would have to think about that. There's certainly mechanisms that can be developed or used. Within the agent, there is a function that basically turns off and turns on the actuation. Now, this is done by another agent that basically sends a message at a certain time. This is a manual process that we've set up. Then this is for us to leave our TCC applications running and going and producing demand curves, but not actually actuating. And so we'll basically send out this message that says, okay, it's time to start doing controls. And we'll run that for either a day or a couple of days, depending on the test length that we want to conduct. And you can target that to specific VAVs or specific zones if you desired, but we've never done it for the use case that you're mentioning, whereas we want to just turn off periodically throughout the day. But that could definitely be accomplished using that mechanism. You just have to put a little bit of thought and modify that messaging agent that we've created to basically, instead of just firing whenever it starts, to fire based on some schedule. And
hey, Robert,
if anyone, yeah, go ahead.
Can you, on your PowerPoint, can you bring up the price capacity curve?
Sure. Which price capacity? This guy?
Anyone, yeah.
Okay. Yeah, there you go.
So let me get rid of my, okay. So there are a couple of ways we could do that. One way is by changing the temperatures, as Robert explained. But there's also this factor K, which is basically a sensitivity parameter that actually stretches the flexibility. A K of 0 would yield maximum profit. That means you're willing to take any amount of discomfort. And then a K of very high value would means that you don't have any ability to flex. So currently we only have one value of K per zone. However, if your judge has, different, or you want to manage that judge's office differently, you basically make that K as a function of time. And then that would handle that case. And then your third question about overrides. We do a couple of different ways we override. One is a global override where the building operator can basically override the entire building from responding to any of the actuation signals that Voltron sends. And then and we only support BACnet. So in BACnet, there's also ability to provide individual zones a priority, or we can override the set points at certain priority. And then the operators can come in and override that because they have a slightly higher priority than Voltron does. So that's another way an operator can basically override certain zones. And I don't remember your second question.
I think the opt-out and the agent priority, and then there was a comfort limit. You covered that, and also I don't know. Maybe that gives me some sense of the way it could work around. You're saying that the Voltron will work, and then as part of a larger control scheme, it's overridden at times as a control function by the larger operator or system.
They have the ability to do that. And they can do that for the whole building or for individual zone.
So still, yeah, it really depends on where you want the opt-out to be. If you want that to be at the application level where you're handling that at the VAV, you can do that as well by turning off actuation. And I already mentioned that there's a mechanism for sending a message to the agent that basically turns off actuation. Or if you say, okay, we don't want to turn off actuation for this agent, but the building operator at the BAS, as Srinivas mentioned, they can selectively pick certain zones. Say they know that a conference is happening in one of the rooms. They say, okay, we know that we want to keep this set point at a certain value during this conference. Voltron writes at a BACnet priority that's lower than the one used by the operator. So if they controlled that point, they would basically override the Voltron controls, and the controls that they elicited would be used instead of the Voltron controls. And then when the conference was over, they could release that value, and it would re-enter into the to regular the market service.
Yeah. So what the BACnet doesn't have is the understanding of the market service and how to really adequately participate in the market with so many different devices. That's what the difference.
Well, BACnet is just a communication protocol.
Yeah.
Yeah. So basically, it's just a way to package the information from the building automation system in a standardized way that different entities and different devices and things like Voltron can utilize that data and for interoperability, really.
Yes.
So.
Okay. Yeah. So when you were given the whole slide set, who was the audience, and how did you decide to work through all this? I mean, was this for the whole campus buildings kind of a review process that you were going through, or what?
When what?
The slide set that you're working through here.
Oh, so basically we wanted to present some of the applications, and so last week we presented a few of the applications that we use, and I'm actually more familiar with the applications that were presented last week. This was one of the remaining applications that we've had in active development for quite some time, and so we wanted to talk about it, share some of the information about it. And I just utilized a slide deck that had been created for another audience at another time to basically show off some of the stuff that we've done with TCC and give you some of the information about it.
Okay.
Yeah.
Yeah.
Does that answer your question?
Yeah. It looks like there's lots of great detail in there, you know, and maybe hard to pick up.
That's why I skimmed over some of it. Some of it I'm less comfortable with, like talking about some of the structures of the models and stuff like that. And I just kind of wanted to give a high level overview and also kind of let people understand the structure, and mainly let people know that if they're interested in deploying or utilizing this technology, that there's support here at PNNL, and that we can also, you know, in the form of, you know, information and also tools to help configure and deploy these things.
Yeah. Well, I know there's some projects that DOE's coming up with to submit for advanced communities, and they're looking at you know, building controls and probably also residential type controls. And I would think that they would be interested in employing these kinds of things in that that I guess request that's due the 15th of May, I think. Do you have any inquiries related to you know, that advanced or smart communities type work?
I have no idea. Sernavos, do you know anything about that?
Yeah, we are working on a number of different things, but I don't think there is anything that we can share at this point.
Okay, so what, you become part of the team as a resource team or that sort of thing? Yeah.
We don't know whether the labs can lead, but we know labs have to participate because if one of the required stakeholders is a national lab. So yeah, we are in discussion with a number of teams.
Okay. I was just curious how that worked, because it looks like what you would like to do, and I mean, from a utility perspective, is employ as much open code to allow, you know, competition in the future. So one of the big drawbacks of so many things is getting locked into some mechanism that's proprietary, and that's easy to do. And so you like to employ and build upon open system to the degree that you can. So anyway, just curious. Thanks.
Cool, great questions. Thank you.
One more question, Michael Hammersley. Question on sort of regarding the setup for these sorts of agents. I know that there's like the reference app, for example, has some pretty rigorous documentation to get some of that running. Is there similar documentation of like, here's how to use these agents, here's how we expect them to work in concert with each other, that might be available to spin up an instance with them at all?
We're in the process of developing like you know, both the configuration tools to aid with the configuration of these applications, and some documentation around that, and the use of the applications. So that's in the works, and as those become available, we'll definitely share those with the community.
Cool, solid, thank you.
Yep.
Quick question.
Sure.
Have you had any luck extending those models to the dual max VAVs?
We are currently, good question. We are currently working on that, and I believe Sen has a methodology in mind. We need to do additional testing and validation that those actually work correctly, and then update our code to allow for the dual control for both heating and cooling simultaneously. So the answer is we have recognized that it's a need, and I think that, you know, we recognized it prior to, this is Dave, right?
Yes, it is.
Yeah, we recognized it prior to you. Previously, I know as you deployed this, you recognized that as something that you needed for your campus deployment, and we had seen that as an issue previously, but we hadn't run into any encountered it. But we're definitely looking at it.
Okay, well, let me know when you have something you want to validate, and we've got some stuff we can validate it on.
Cool, that would be great.
Yeah. Also, any chance you guys can share this slide deck?
You'd have to ask Srinivas. Is that? I don't have an issue with it, but
Isn't that on the Voltron thing?
this slide deck is part of a set of slide decks that we generated for a DOE visitor. I want to say a year or so ago, a year ago.
Yeah, Dave, ping me later. I'll
Okay.
check what is, because there are, you know, some of these slides have building names and references, which we really don't want to get that out.
Okay. Will do. Thanks.
All right, any other questions? If not, maybe Robert, could you bring up the GS repo again, just so that you kind of talk to people about what's in it?
You want me to talk on what's on it, or just?
Yeah, just to give some background on the purpose of this repository.
Yeah, so this is going to be the repository that all of our applications live. We have another repository, the Voltron Dash applications, with a couple of our fault detection and retuning diagnostics that are still there, and we are going to migrate those over here as well. So this will be where all the PNNL applications are going to live, and within this we have the TCC, which is the market agents. We have that model regression agent that I discussed, which is intended to automate the training and retraining of the different applications within the TCC structure. We have the intelligent load control, which we talked about last week. We have this, what we're calling the TCC ILC, which is essentially a agent that allows for creation of price capacity curves for the building level to communicate a demand target to the ILC agent. So it's essentially allowing the ILC agent to interact with transactive markets. And then we have, we're going to migrate our economizer and our retuning applications into this repository as well. So this Voltron GS will be where the PNNL apps that are currently being supported will live.
Okay.
Oh, it also has, this is just to mention, it also has our Energy Plus agent and our recently developed Modelica agent for doing co-simulations with those two platforms. So, is that what you're looking for, Jeremy?
Yep.
Cool.
All right, thanks. Any other questions? Robert's presentation of the other applications last week should be getting posted soon, along with this one. So you'll be able to catch back up if you missed one. I guess, Robert, the slides from last week, could you check if those are also shareable?
They're from the same set of they're from the same
Okay,
set
same
of
visit. Okay.
same set of presentations. So I mean that would really be I mean they have the video, so
Sure. Yeah. Okay.
I have no problem with sharing them. That's really up to like Srinivas and I guess the release process. I'm not sure.
Right. Okay.
Yeah, well, we'd appreciate it if you'd ask him.
Will do. Okay. Well,
All right, thanks guys.
Yeah, thanks a lot, Robert. That was great.
Thank you.
Yep. How do I stop sharing here?
Don't stop sharing.
There should be, yeah, there you go. So yeah, thanks, Robert. And so I'd like to encourage everybody on the call, if you have research or use cases that you'd like to share, that would be great. So even if you don't have a completed application, if you have a use case, this is where we're using Voltron or thinking of using Voltron, or this is a problem we have in the building space, and would be willing to present that at a future office hours, please contact me. These are the presentations that are really interesting. Get across the potential use cases and opportunities for collaboration across people on the call. So yeah, please let me know if you have anything that you'd like to talk about, and we'll make time for you on a future office hours. All right, well, we've got about just a few minutes left. Open it up are there any questions people have, either for Robert or just in general?
I have a question.
Sure.
So recently had some need to characterize things about some of the Voltron systems that we're running as we're trying to figure out exactly what resources they're using as we're moving those over to virtual machines. So I need a little bit of extra functionality compared to what's in the Sysmon agent, and was adding that there. Something I noticed is that it publishes on a data logger topic, but it simply publishes a float as opposed to a readings dictionary, which just kind of generates an error every time it publishes from any historian that's running. I'm guessing that probably wasn't the intended functionality. And so I was kind of wondering if that were corrected to kind of use the data logger, the standard message format that the historian picks up for the data logger. Is that going to break things for a whole bunch of people that might be monitoring that elsewhere? Not reading it into a historian, but just subscribing to what's there. Do you know how much that's actually used, or any thoughts on how that would be best handled?
I don't think that would, anyone correct me on the call. I don't think that would break anything for anyone. And Shweta, James, weren't you looking at this?
Hello, this is Shweta here. Yes, Roshan Kenny had mentioned this earlier this week. Unless others are using it currently, I don't think this agent has been used by many people in the community. So I would say go ahead and make the changes.
Okay.
Yeah.
Okay, I just wanted to make sure that if it required that functionality to be preserved in its kind of current state, that it would require adding an extra flag or something to to keep
I don't-
that. If
I don't
that's
believe
not
so.
going to break things for people, then.
And we can announce on the mailing list when, when that change gets implemented, and let people, if anybody, if that impacts someone, then we can go ahead and enable that.
Okay. Great, thanks.
Yeah, thank you. Anything else? All right, if not, we'll call it an office hours. Thanks again, Robert, for presenting. And if people have topics they'd like to see covered in future office hours, please drop us a note and we will make that happen. All right, thanks everybody.
Thank you.